Hello everyone, my name is Bingquan. I'm from Peridynamic Research Center based in the University of Strathclyde in Glasgow. Today, we would like to present our research on the closed-form dispersion relations in the bond-based peridynamics. Before the presentation, I would like to acknowledge co-authors Dr. Selda, Oterkus, Dr. Erkan, Oterkus for this study. Presentation is broken into four parts. The peridynamic theory is introduced at the beginning. The dispersion relationship formulation based on the bond-based peridynamic theory will be demonstrated in the second part. Afterwards, the numerical simulation of the material dispersion will be presented and compared with experimental data. In the end, the final remark will be discussed. In this section, I would like to give you a brief introduction of the peridynamic theory. Peridynamic is a new continuum mechanics formulation. The classic continuum mechanics is proposed by the French mathematician Augustin Cauchy. It assumes a continuous body under smooth deformation with a differential equation. Since there are no partial derivatives defined with respect to the discontinuities, so the theory has constrained the formulation of discontinuities in the damage and failure problems. Dispersion curves that describe the relations between the wave frequency and the wave number are linearly according to the classic continuum mechanics. However, based on the experimental dispersion relations obtained by inelastic natural scattering, we found most of material exhibit nonlinearities at a small wavelength. So the classic continuum mechanics fail to predict this phenomenon because it doesn't have a length scale parameter. Non-local continuum mechanics is being extremely popular in the development of the new materials and systems, such as carbon nanotubes or the graphene. Peridynamic is a strong non-local theory which proposed by the Dr. Selim in 2000. He is a distinguished researcher at Sandia National Laboratory in the United States. It employs a non-local model of force interaction and replaces the partial differential equations which can model the crack of the structures in a spontaneous way. It also has a length scale parameter called Haugen size, which defines the non-local interaction between its surrounding material points, which can be captured the elastic behavior over the wide range of the length scales. So let's have a look what is peridynamics. Peridynamics is a physics of a material body at a point that interacts with all the points within its range. As can be observed in this figure, the structure is discretized in a series of material points. The material point can interact with other material points within a range. The range that the material point interacts with other is defined as horizon. Any surrounding material's point beyond the horizon range, the material will lose the interaction. The bond Cauchy is defined a position vector between two material points in undeformed configuration. In this figure, the Cauchy presents relevance between material point x and x prime. Why Cauchy represents a position vector between two materials in a deformed configuration? The equation of motion at a material point x in peridynamics is an integral form. The bond interaction F is in the equation of motion is exchange of force between any pair of material points. As shown in the figure, in the bond-based peridynamic model, the pairwise force density vector is equal in magnitude but in an opposite direction. The force density vector in each bond is explicitly related to the bond constant and the stretch. The bond constant is linked with material constants from the classic continuum mechanics. The stretch is defined as a position vector between two material points in a deformed configuration divided by a position vector between two material points in an undeformed configuration. In the second part, I would like to explain how to drive the closed-form dispersion relations in the bond-based peridynamics, which will be demonstrated in the one-dimensional, two-dimensional, and three-dimensional forms separately. As mentioned in the second section, the pairwise force density vector between two material points within the horizon size can be related to the bond constants and the stretch. More specifically, the stretch is related to the displacement field of the parallelized material points and their position vector in an undeformed configuration. Since we are focusing on the dispersion chapters of the waves based on linear peridynamics, to access the wave dispersion, we are using harmonic plane wave solution for the displacement field of the material points. Well, in the plane wave solution, Q represents the response amplitude, K is the wave number, X the position vector, and omega the angular frequency. By using the plane wave solution, we obtained the displacement field for the material point X and X prime, substituting them in the stretch and then into the equation of motion. We can find that the equation becomes an integral form with a cosine function over the horizon size. In the one-dimensional case, the bond constants for the isotropic material is given, where A is the area which can be cancelled with the area in the equation of motion. Once we solved the integration part in the equation of motion, an explicit solution can be found for the peridynamic equation. At this point, we have founded relations between the angular frequency and the wave number from the peridynamic equation of motion, which represents the material dispersion for a one-dimensional structure. To validate our dispersion relation, let us consider a relation between the peridynamic theory and the classic continuum mechanics. The cosine function can be expanded with Taylor's function with considering first two terms, substituting into the equation of motion and performing integration, leading to an approximate form of the dispersion relation. As mentioned earlier, the classic continuum mechanics doesn't have length scale parameter, while the peridynamics does. So let's reduce the horizon size to 0. As we can observe in the equation, the peridynamic dispersion relations become to the dispersion relations in the classic continuum mechanics. The dispersion relations in the two-dimensional structure follow a similar procedure with our one-dimensional case. First, we also need to find the total stretch between two material points. The displacement in the x direction for the material point x and x prime can be represented by u and u prime, while the v and v prime for the displacement in the y direction. Therefore, we can find the total stretch for a bond. Considering the wave propagation in the longitudinal direction, the v prime minus v times cosine theta is equal to 0. So we can find the total stretch between a bond in the longitudinal direction is the total stretch times cosine theta. Similarly, the stretch in the transverse component is the stretch times sine theta. It would be easy for us to carry the integration of the equation if it is written in a polar coordinate system. Substituting the stretch we found into the equation of motion, we now have two equations in the longitudinal and transverse direction in a polar coordinate system. In two-dimensional case, the bond constants for the isotropic material is given, while h is the thickness which can be cancelled with the thickness in the equation of motion. By solving the integration parts in two equations of motion in the previous slide, now we have the wave dispersion relations in the longitudinal direction and the transverse direction. To obtain the dispersion relations for a three-dimensional structure, first we also need to find the total stretch between two material points. We use U, V, and W present the displacement in the x, y, z direction respectively. We first found the total stretch mapped on the x1 plane and then drive the total stretch in the xyz coordinate system. This is the total stretch between polarized material points has been found. By applying the trigonometric functions, we can find the stretch in the longitudinal, transverse, and vertical components. Again, it will be easy for us to carry the integration of equation if it is expressed in a polar coordinate system. Substituting the stretch we found in three components, we now have three equations of motions. Here, we also have the bound constants for the isotropic material in three-dimensional structure. Substituting the bound constants into the equation and solve the integration over the bound distance, now we have the wave dispersion relations in three separate directions. The closed-form dispersion relations in the bound-based peridynamic has been obtained in the previous slide for the one-dimensional, two-dimensional, and three-dimensional structures separately, all of them which are in terms of material constants, density, and the peridynamic length parameter, which is horizon size. In the third section, we would like to examine our dispersion relations based on the material experimental dispersion data. Isotropic material, silver, with a face-centered cubic structure, has selected to examine the dispersion relations obtained from the peridynamic equation of motion. The material properties of the silver are present in this table. Now, we are going to substituting these material properties in our dispersion relationship for one-dimensional structure. As can be seen from the figure, when appropriate horizon size is chosen, such as 2.513 to the power of -10 for silver in a one-dimensional formulation, the peridynamic dispersion has a close agreement with experimental data. In a two-dimensional case, the horizon size 2.715 to the power of -10 can provide a close agreement with experimental data in the longitudinal direction, but limited match with experimental data in the transverse direction. Now we are going to make a final remark for this research. With original bound-based peridynamic formulation, the peridynamic dispersion relations has been derived in 1, 2, 3-dimensional. It has nonlinear forms in the peridynamics, which is horizon size, so the real material behavior can be represented for the small wavelengths when approximate horizon size is taken. That is all from us for today's presentation. Finally, we would like to acknowledge the US Air Force for the financial support for this research. Thank you.